come to the Vintage Computer Festival at the Enter Museum to see the evolution of From the Hole to the Cloud.
Okay, another good morning to another exciting talk. Welcome again, those who were at the previous talk. Now we go more into depth into how data was transferred from a PC to a MiniDisc and vice versa, probably.
Later on, yes.
Later. And so Piotr Kumka, also known as asivery, like if you go on Reddit, he's quite active there. I saw like you reconstructed the OLED display of display, like beautiful.
That is part of this picture here, of course.
Yeah, lovely.
This is the screen.
So without any further ado, Piotr, and if you have questions, feel free to ask them afterwards. So thank you.
Well, thank you very much for coming to the talk. First, a few words about myself. I am a developer of open source software for both old and new hardware, and sometimes I write software which acts as the bridge between old and new machines. I've become interested in MiniDisc approximately like 7 years ago. I got my first device, this little MZR3, at a flea market after being introduced to the format by a YouTuber called Technikwelt and his wonderful video about the format. But that's enough about myself. Let's jump to the main point of the talk. So NetMD. On the screen right now, you can see the 4 first-generation devices of which support the NetMD protocol. NetMD is Sony's way of transferring audio and data from a computer to the MiniDisc device. At least that was the point at first. These 4 devices all are equipped with a USB port, and they talked to an application on your computer called SonicStage. SonicStage was responsible for enforcing the DRM as well. So let's talk about the protocol and how Sony actually intended to have it be used first. NetMD is based on FireWire's AVC, so Sony basically took a protocol for FireWire and then made it work on USB. It can transfer audio to the disk, but it cannot transfer the audio back from a disk to your computer. At least that was the original intention of Sony. It can manage existing tracks, so you can rename them, shuffle them around, but not splice them or cut them in any way, which actually is possible in the MiniDisc format. It's just that Sony didn't implement it. It also manages the DRM thanks to the OpenMG system. And the OpenMG, there is actually nothing open about it. I don't know why Sony called it that way. It's Sony's naming. If you're familiar with their modern headphones and things like that, you'll know their naming hasn't improved since then. They still don't make any sense. And that's the important part, the last one. The original Sony software only allowed you to make 3 copies of any track you added to SonicStage. So you could put 1 track on your disk, then put another copy of that same track on a disk you gave to your friend, and maybe to your friend's friend. But if you wanted to make another copy, you had to take that disk, put it into a NetMD device that's connected to the same computer that's running SonicStage, and then from SonicStage erase that track, and that frees up that one of these 3 slots. So you can reuse that slot and put the track on another disk. So, of course, since that DRM was so restrictive, many open source developers, even back then, even back in 2001, back when NetMD was released, started working on open sourcing this. So this is the rough timeline of the events that are, in my opinion, the most important to NetMD in general. In 2001, of course, Sony released the first generation devices. In 2003, a project called FreeMD pops up, and it starts documenting the protocol. They documented how the commands used to manage tracks actually worked, and not how to actually transfer audio to the disk. In 2004, libNetMD implemented what FreeMD documented. So FreeMD didn't in any way implement a program which made it possible to control your device. They only documented everything. In 2008, Linux MiniDisc got created. It got started by 2 people, Adrian Glaubitz and Michael Kerher, but of course later other contributors joined in, people going by the pseudonyms THP, Nopsled, and many others. But Linux MiniDisc was created mostly for the second generation of MiniDisc devices, the high-MD devices. And it was originally intended to allow you to put audio on high-MD discs. It only later expanded on the work created by these other projects that documented the first generation protocol. But still, we are in 2008, it was still impossible to transfer audio to the NetMD devices because of the DRM. People didn't understand how the DRM worked. And this is where we get to our first breakthrough. In my opinion, well, this is one of the two most important events. In 2010, Michael Kerher, one of the creators of Linux MiniDiscs, manages to transfer audio from his computer over to the MiniDisc device without SonicStage. So he reverse engineered enough of this DRM that Sony baked into the standard to actually circumvent it and get his audio onto the device. And here I have to elaborate a bit because the format NetMD uses is backwards compatible with older MiniDiscs. So if you got an original MZ1 back in 1992 and then in 2001 you got one of those first generation devices, you are still able to put audio onto that disk and then put that disk in the first generation device, the one from 1992, and it will play back. So even though this data is encrypted while it's being sent, it's not actually stored as encrypted data on the disk. It gets decrypted by the device as part of the recording process. Then in 2019, Platinum MD got created, and these events here I call the new era of MiniDisc software. All these applications here that are mentioned are written basically in JavaScript. Platinum MD was written in the Electron framework, so it essentially bundles a copy of Chromium with some native components and makes it possible to easily talk between the native part and the browser part. And of course, in 2020, Web MiniDisc got created by Stefano Brilli. Web MiniDisc is essentially a rewrite of Linux MiniDisc into JavaScript that utilizes the Web USB API, and that makes it possible to connect from Chromium directly. So you can open Google Chrome, go to a website, and it will prompt you whether or not you allow this software, this website, to talk directly to a device. Then in 2022, we managed to dump the device's firmware and create a library for managing exploits and advanced features, thanks only available to modifying the firmware, but I'll elaborate on that later. Let's delve back into 2010 and see what exactly, how exactly the DRM works. So, the OpenMG system works on files called EKB files. These are enabling key block files. They contain the root key used to encrypt the track key that actually encrypts the audio while it's being transferred over USB. As you can see on the slide, there are many ways, many routes to basically derive the root key depending on what device key you have. And one device key was supplied in SonicStage. These files were part of the SonicStage and OpenMG codebase. And every time you transferred an audio file to them, these devices, the OpenMG software had to basically derive all these keys, then basically have one key decrypt, another key decrypt, another decrypt, another, and reach the root key, which ultimately encrypted the random track key, and the whole key chain used to discover this root key and the encrypted track key and data encrypted using this encrypted track key got sent to the device, and then the device decrypted it. So you can see this is somewhat complex, a lot of decryption and encryption going on. It's not really, it wasn't meant to ever really be reverse engineered. This OpenMG system uses very complex tricks so that these keys don't leak. Like Sony actually made a virtual machine that runs their own proprietary bytecode. So what did Michael Kerher do in 2010 that circumvented this? He basically abused the keychain mechanism by adding in another known key to the end. He made the system think the root key, the original Sony root key, was an intermediary key, and made it so that the root key decrypts another key that he created, and that key was in no way random. It was just 1, 2, 3, 4, something like that. It was just a sequence of numbers. Then he derived the root key somehow, encrypted that known key with the root key, and created this encrypted modified keychain. Then, because then the new root key was known and, well, he owned it, he could actually separate these two parts entirely, send the known keychain that was extended with the new key to the device, and then use the known plain text version of that root key to encrypt that random track key and send it that way. So this made it possible to add normal audio upload to MiniDisc devices without SonicStage and without all this DRM. You can see that we do not need to go through the keychain again. That has been done already. And sending that particular keychain to the device doesn't require you to actually process it on the computer. The device does process it because it thinks it's valid Sony EKB, but it's not. And this is entirely separated. And what's interesting here is that this doesn't really infringe or break Sony's DRM in any way. Because the root key was never published, it doesn't weaken the inherent security of the system. So it was a very nice point at which he could basically publish this, because it didn't infringe on anything. So now let's go to the next breakthrough. This screenshot comes from a Sony service manual for one of the higher-end NetMD devices. This is a patch writer, an application used by Sony to update the device's EEPROM with tiny patches that basically allowed them to fix some firmware flaws. And this software hasn't really been noticed before, from what I know. In 2022, the screenshot was brought to my attention by a member of the MiniDisc Wiki Discord server named JDub, I believe, and he asked me whether or not I've seen this software before. I of course answered I haven't, and I tried looking for a copy of it. Unfortunately, it was removed from Sony's website, and the Wayback Machine hasn't archived it before it was released, before it was deleted by Sony. But thankfully, we managed to get in contact with a user of the Sony Insider forums. So these were the older forums before even Discord was a thing. It was for the people who were originally interested in MiniDisc, NetMD, and stuff like that. His nickname was SFBP, and he actually had the copy of this software archived, and he sent it to me. I managed to reverse engineer part of this software that was responsible for sending these commands to the device, because I was curious how exactly it was updating this. And this has basically led finally to dumping of the firmware. Before we dumped the firmware, we tried sending little patches to it. Me and another contributor, another reverse engineer named Sir68K, we both worked on dumping the firmware. We didn't really have like a competition around it. We didn't have a race, but we were both trying different ways of dumping the firmware. So I was trying to do a side channel attack where I varied the device's power usage according to whether or not the currently read firmware byte was a 0 or a 1. And he went for the much smarter approach of actually trying to locate the USB buffer in the memory of the device, in the random access memory. And he of course succeeded. And he dumped the first copy of the NetMD device's firmware over to a computer. So after we had the firmware, we of course started reverse engineering it. This is a screenshot of a tool called Ghidra. And this is what we use for reverse engineering the firmware. It has a feature where you can set up a collaboration server and have multiple users work on the same file and reverse engineer the same firmware. So we of course set this up, and Sir68K delved straight into how the operating system of this device works, so the real-time operating system. And I started reverse engineering the USB code, which you can see on the screen right now. This is part of the USB firmware of the NetMD devices. Ultimately, Sir68K managed to find exactly what this patch writer software was invoking in the low-level APIs of this system, and he managed to create a proof of concept where he wrote the patches to random access memory, so that if something went wrong, the device could be restarted and it would basically return to normal. So we could easily, thanks to this, play with the firmware, patch it around and see what exactly the results were. And if we didn't like it, if we didn't like the changes or something broke, we could always reset the device and go back to a known standard state. So how exactly is knowing the firmware actually helpful in developing new features for MiniDisc devices? Well, first of all, we need to discern between these devices. These are the main firmware families. that the tool used to exploit these would have to handle. So of course we have the first generation devices, the second generation that came a year later, and then the newer second generation MiniDisc devices, so high-MD. This is the Type S devices are second generation NetMD, but they still use the same discs. But these things, these devices right here, high-MD devices are compatible with a new standard of discs entirely that's not backwards compatible. And you can see the differences between these devices. You can see how little RAM there is to work with, because in the first generation, only the SRAM is memory mapped. So you can only write code or patch the code thanks to SRAM. Because the way these patches usually work is the actual firmware is stored in ROM, but we can influence some few blocks of ROM only. So, for example, 4 bytes is the minimum amount we can patch. So we can replace any 4 bytes with any new 4 bytes, and we have 8 slots. So it can be in any place they can be stored in the firmware. But 32 bytes or something like that isn't really enough to write whole new features. So we usually just add a jump to RAM and find 3 places in RAM where that code can be stored. And that's how everything works. So we still need the RAM, and you can see the amount of RAM in the first generation of devices is actually dire. Pretty much nothing fits here. These new high-MD machines, the DRAM is also memory mapped, so that's no longer an issue. But yes, since we now know the differences between these devices, we can try to write a library which acts as an intermediary between a generic exploit code, so a generic feature that we want to add, and the devices themselves. So I wrote such a library. It's called NetMD exploits, and it's written in JavaScript because it extends the features of the web application I mentioned before. So you can see the 3 main components of this library. The device state manager actually handles the firmware versions and the hardware revisions of these devices. The exploits are the main features, so they are, of course, what we're all here for, the new features that we want to add to these devices. And the assemblers are used to, well, assemble the code of the exploits and make it possible to run the code on these devices. So this is NetMD exploits. And now I wanted to delve a bit more into how these exploits work and show what exact new features can be added. So here is the code for a track upload. And marked here, you can see an if statement, which checks whether or not the data we're trying to send is SP, LP, or LP2. These are the 3 codecs that Sony wanted people to use while transferring data to NetMD. You couldn't use mono, which is, of course, possible in the older devices, because Sony really wanted you to stop using mono and only focus on LP2. Well, what happens if you remove this check? Mono upload starts working. So this is one of the things that Sony just locked down because they felt like it. The code is entirely compatible with mono, but Sony just felt like not allowing users to actually use their devices the way they wanted to. So that's typical, I guess. But more typical of modern times than these older devices. I guess some things never change. This is an example of a really simple exploit. Removing this if statement is just 1 command, and of course mono upload works afterwards. And now for an example of a more complex exploit. This is the way the data is stored on the disk. You can see that a sector consists of 12 sound groups, some data at the front, and an epilogue. And we need to know how exactly this works so that it's possible to recover data from a MiniDisc device via NetMD and send it over to the computer. As I mentioned before, Sony really didn't want people to do that. They locked it down and made it so you could only transfer data from your computer to the disk and in no way send it back. They actually made it possible to do that only in the final device they made, the MZRH1. But this can, of course, thanks to exploits, be circumvented. But to circumvent it, you need to know the exact layout, and you need to know exactly which sector comes after which, to be able to reconstruct the final sound stream, the final compressed audio stream of that track you are trying to dump. So for this, we need to use the table of contents. This is the table of contents is the two tables I added at the bottom of the presentation slide. The first table is the link table. It maps the track number to the first fragment of that track. And the fragment is a bit of contiguous audio that spans a sequence of sectors on the actual disc. So here you can see I've given an example of, for example, track 16. This is the 16th cell of that table, and it points to this cell in the contents table, and that cell contains the first two records, so from sector 304.070 to 408B, and it says that the next cell is that one over there, and that cell contains the second record. So you can see this is the first set of contiguous audio, and then this is the other one. So knowing these, knowing where exactly, on which sectors a given track is located, we can find that track in the DRAM of that device, transfer the whole DRAM back to the computer, and then stitch the audio sectors so that the final audio stream matches the order that the sectors are supposed to be placed in, dictated by the table of contents. So the exploit here is used to transfer the audio back to the computer, but in an unorganized form, and then the code on the computer actually organizes the audio, and if needed, flashes the buffer and then rereads it. This is all possible thanks to the fact that MiniDisc devices have something called an anti-shake memory. The anti-shake memory was used so that if you were, for example, jogging or exercising and the device was shaking in your pocket, the audio didn't skip because it buffered a large chunk of audio onto the device's RAM and then played audio back from that RAM. But of course, this can be exploited. If we have the RAM and we have access to the RAM, we can just send that data to a computer and restitch the audio as Sony devices usually do when playing the disc back. So that's essentially how we managed to circumvent the copy protection that prevented you from saving and archiving your audio via NetMD. You can see it was a lot of work by numerous contributors. Of course, the Linux MiniDisc project, the FreeMD, which documented the standard, things of this sort. And all of this is now packaged into a web app called Web MiniDisc Pro, which is the fork of the original Web MiniDisc created by Stefano Brilli in 2020. The only difference is that, of course, Pro contains this code, this NetMD exploits code. And as a final part of the presentation, I wanted to just bring it to your attention how many interesting things can be reverse engineered from MiniDisc devices. You, of course, have the MiniDisc format itself, the way data is stored on the disk. You can reverse engineer the OLED controller that controls the display in the case of this MZRH10 device. You can reverse engineer the UI controller itself because Sony, of course, had to overcomplicate it. And they made it so the UI is handled by this separate chip, separate to the chip that controls the device itself, the firmware and the disk and, well, USB transfer. Then, of course, you can you can reverse engineer NetMD and HiMD protocols. That's what I described today. Of course, I didn't really delve into HiMD because of the time constraints, but I feel like NetMD is interesting enough on its own. And of course, there is also the inline remote protocol. The inline remotes were these tiny remotes you could clip onto your shirt, and they had little displays which showed the currently playing track, the title, etc. So this can also be reverse engineered. So even though this format has been dead for a long time now, there is still plenty of interesting things about it. So that's all. Thank you very much for listening to the presentation. I hope you enjoyed it. Please let me know if you have any questions.
Yeah, thank you for that hacking tutorial. I just thought, like, have you yourself, like, were you able to transfer something thanks to your software now that you weren't able to transfer before?
Yes, so Sony software didn't really allow you to transfer audio from the disk to the computer, but as I pointed out in the presentation, if you know the layout of the track and you have access to the memory, you can dump that audio and reconstruct it. So it's possible to now dump audio from many devices, pretty much all NetMD devices, except, well, one, the MZDH10P, the weird camera, because that still hasn't been really exploited and delved into. But I feel like that's not a device that many people would even use for that purpose.
Yeah, any questions? Please.
Hi. Before the USB protocol with the NetMD exists, there was also from Sony a device, MiniDisc data.
Yes.
It was a portable SCSE device. There was also possible to read out the discs as a. I know it because
Yeah, the raw data. I know, but I didn't really explain much about it because it's not really related to NetMD. This device was really rare, so not many people bought it.
I have one.
Oh, congratulations. These are very rare now. And if you have one modified to actually allow you to copy audio from the disk, then that's even rarer. Because not many people bought I think it was called the MDH10. Sony MDH10.
Yeah.
Not many people bought the device, and even less people bought a device and then modified it to actually allow you to dump audio like that. So if you have one equipped with that, then congratulations, you have a really white whale.
Okay, good. But this was what I note because also NetMD, as a not before NetMD, the MiniDisc was also used as floppy replacement. It was original was the intention from Sony to use MiniDisc also for the computers, but it was too expensive and the patent. They don't open the patent for the.
I see.
This was the problem.
Yeah, so this was MD data.
Yeah.
It was separate from MiniDisc. It uses a different format and different disks.
120 megabytes was for the data.
Yeah, it now seems tiny, but back then, when you were competing with a floppy disk that had like 1.4 megabytes, then of course, over 100 megabytes is incredible.
But I have only one disk device and one disk, not more. So pity.
Yeah.
Okay, well, a wonderful presentation.
Thank you so much.
Yeah.
Thank you. I have a question and an anecdote. I think I was talking to you about it outside. That I remember my first time getting a NetMD device, and I was working in student radio at the time, so we had used MiniDiscs all the time. They were perfect format. And I remember one of the sticking points was that we needed to pull interviews and audio off MiniDiscs into Audacity on a PC. So we'd have to sit there with it playing for like an hour long and come back to it later. So when NetMD came out, I was like, fantastic. Now I can finally just plug it in and rip all my interviews on. And I remember my first time getting SonicStage and plugging it in and playing around looking for where's the download? I can't.
Yeah.
And then realizing it wasn't there and cursing Sony for it.
Yeah.
So that's my anecdote. But my question is, your work is amazing. Did Sony come after you for any of this, or all of the patents are out, or they just are not interested?
I don't think they are interested. The code for HiMD, part of the Linux MiniDisc code for HiMD, actually contains the key, because while Michael Kercher was able to do that trick with stitching the final key at the end of the keychain in NetMD, that's not possible in HiMD because the EKB files are signed. So if you don't have the private key required to re-sign the file, you cannot alter it in any way. So this code base contains a key, and Sony didn't come after them, and Sony didn't come after the firmware or none of these applications. So I think they just don't care anymore about this. But
And I suppose a second question, did any of the developers from Sony in Japan contact you, or anyone? No, at all.
No.
That's amazing to me, because developers always like, especially guys who made stuff 20 years ago, they love talking about that. Nobody contacts you.
No one.
Okay. Thank you.
Thank you for the questions.
as an anecdote, I also had in the early 2000s Sony Bio PC. I remember it came with SonicStage, I think you mentioned, no? And
Yes.
I tried to rip all the music. Like they were offering as a way to copy the music from your main PC into the micro PC. And it turned out that I ended up with a bunch of OMG or an OMAI files.
Yes.
So they were not using this scheme only for MiniDisc.
Yes, so OMA files, they actually they can contain the DRM, so probably Sony also, while you were transferring your audio, they actually put the DRM onto your files. They were so kind to actually encrypt them for you so that you cannot recover them if something went wrong.
Even though they were already digital music files
Yes.
from this first computer. So
Sony had an issue where they really liked to take control over files they did not own back then. I feel like this was the case also with the scandal about the rootkits in Sony CDs back then. Yeah, they had some draconian DRM back then.
I had also one question. So you mentioned at some point that the new program is based on JavaScript, right?
Yeah.
So it's using the Chrome. So they allow accessing random USB devices now?
There is an API for that, Web USB, and if a website asks for a user to connect a USB device, there is a pop-up in Chrome saying that site something wants to connect. Choose a device to connect to, and if you then choose that device, then Chrome cedes control over that USB device to the website directly.
How does the MiniDisc NetMD device show up in the PC? Like
it shows up as a device that does not have a driver. It's not a removable storage device or something like that.
Okay.
It's technically speaking, it describes itself as a vendor-specific device. That's the class, USB class. So, HID, so stuff like a mouse or keyboard has its own class ID.
Yeah.
Mass storage has another one, etc. And there is this special class called vendor-specific, and that's what NetMD reports as.
So no standard audio or no standard USB audio?
Yeah, no standard. As I said, NetMD is based around the AVC protocol that Sony basically made work over USB by force. It was never intended to work over USB, so that's basically how it works. It has no standard protocol. Windows needs additional drivers, and if you are on Windows, you need to install libUSB drivers, which essentially move the raw USB handling from kernel space to user space.
Okay, thank you.
No problem.
Okay, then thank you, Piotr.
Thank you very much as well.
For your hard work and everything, and then enjoy the show. Have a nice lunch.
Thank you.